Hi everybody, today is lecture number 4, this is lecture number 4, and today I'll tell you about vectors. I'll review vectors from a geometric point of view. Specifically, we'll talk about lengths, dot products, cross products, and determinants of matrices from a geometric point of view. And then I will derive the formula for the area of a graph. The arguments that go into the derivation are important in themselves, so that they'll show up later, 2 times later in our course, and certainly outside of our course as well. And then to conclude the lecture, I will show you how to compute surface area using this formula in a concrete case. So I'll do an example calculation. Okay, so let's get to it. So a vector is very close, is not very different from a point. So both are described by 3 numbers. This vector v that I drew, this arrow, almost identifies itself with the tip, with the point at the tip of the arrow. So vectors are arrows emanating from the origin, and we identify them with the point where the tip of the arrow is at. And then we describe the vector by 3 numbers, which are the coordinates for that point. There's another perspective that we have to denote for these coordinates, for these numbers, and namely that you can write any vector in terms of 3 standard vectors. So here are the 3 standard vectors in R3, I, j, and k. So I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. And you guys can see that v, the vector that I wrote there, is equal to the number v1 times I plus v2 times j plus v3 times k, right? v1 times 1, 0, 0 plus v2 times 0, 1, 0 plus v3 times 0, 0, 1 equals v1, v2, v3. So I will, in this class, we'll translate back and forth between component notation and and the expansion in terms of these standard basis vectors. The components give you the coefficients in the expansion and vice versa. So we basically have 2 ways to describe vectors. I should also, going back to the relationship between points and vectors. So when I think about a point, I will normally write curvy brackets, and if I'm thinking about a vector, I will write square brackets. The difference is really psychological, but I think it's a useful one. Okay, so now let's start putting some useful information together. The first piece of information is the length of a vector. So the length of v, I will denote by this absolute, these 2 bars, which usually for numbers give us the absolute value. So the length of a vector squared, so to explain the notation, what I just wrote means the length, oops, I forgot the g, the length of v squared, we can compute it using Pythagoras' theorem twice. Right, by Pythagoras' theorem, the length of v is equal to the length of the base, so the length of v squared is equal to the length of this base of this triangle squared plus the height of the triangle squared, the length of this vertical piece squared. Okay, so we need to know this length down here squared. This we can get from Pythagoras' theorem applied to this triangle at the bottom. So you see that this triangle at the bottom has sides v1 and actually v1 and v2. So the length of the diagonal at the bottom is v1 squared plus v2 squared by Pythagoras' theorem, and then so this is the length of the diagonal at the bottom squared plus this height over here squared. That's v3 squared. Okay, so we have this nice expression for the length of length squared of a vector. Let me just note that this can be written as the dot product of v with itself. Okay, so let's recap the dot product. This brings us to the dot product. So here's the definition. So dot product. So if I have two vectors v and w, the dot product between v and w has a very simple algebraic formula. We take the first component of v multiplied by the first component of w, then do the same thing with the second component and the third component. So multiply the components and add them. And then if both vectors are the same, this gives us the length of the vector squared by the discussion from just a few seconds ago. So the dot product has a very useful geometric interpretation. So let me draw it for you. So if I call this vector v, this vector w, and the angle between them, if I call it theta, then it turns out that this algebraic expression gives me the length of v times the length of w multiplied by the cosine of this angle. Right? It's kind of a miraculous thing, if you ask me, that this if I do this algebraic thing, multiply the components and add them, I will get the product. I will get something related to the angle of the two vectors. So what I want to do now is to explain to you why this is so. So not everybody knows why this is so. So you can feel almost. You can feel you'll be part of a privileged group of people who know why this is so. So here's the explanation. I'm going to look at this other vector here, which points from v to w. That's w minus v, right? You see, if I add w minus v plus v, if I add these two vectors, I get w. Okay, so I look at this vector, and then I ask myself, what is the length of this vector squared? So w minus v squared is, so now there are two ways to compute this. So the first way uses some geometry. So first I'll use the law of cosines to figure this out. So the law of cosines. So the law of cosines is something you can derive from Pythagoras' theorem. Basically, you have to draw a perpendicular over here, and then use Pythagoras on these two triangles. So using the law of cosines, I will get the length of this side in terms of these two lengths and this angle. And the law of cosines is basically a generalization of the law of Pythagoras' theorem. So if this angle over here was 90 degrees, Pythagoras would tell me that this squared is equal to this squared plus that squared. I should have said lengths everywhere. Right? This length squared equals that length squared plus that length squared if this angle was 90 degrees. So the law of cosines adds a correction term for the cases where the angle is not 90 degrees, and this correction term involves the cosine. So specifically, the law of cosines tells me that the length of this of w minus v squared is equal to the length of v squared plus the length of w squared plus 2 times the product of the angles times cosine theta. Right, the correction term involves cosine theta. That's why it's called the law of cosines. And if theta was 90 degrees, then the cosine of theta would be 0, and then you would be left with Pythagoras' theorem. Okay, so that's what we get from the law of cosines. Now let's work out this length using just linear algebra. So this length squared is the same as the dot product of w minus v with itself. So let's work this out. This is w times w minus, there are minus 2 times v times w. So here I noted that there is w times v and v times w, and that the dot product of w and v is the same as the dot product of v and w. You can see that this expression here, this product is commutative. And finally, there's a minus v times minus v, that's plus v times v. Okay, So let's see what we got here. First term is v squared, length of w squared. Last term is length of v squared. And so v dot w is the same as this thing from the law of cosines, which is what I wrote here at the beginning of this derivation. So that's why the law of cosines is true. So this stuff in the left, this derivation, you guys shouldn't worry. This is for your information, but you shouldn't worry about it in exams. As far as exams and the homework are concerned, you should just bear in mind that the dot product sometimes it's useful to think of it as this algebraic formula, and sometimes it's useful to use this other expression involving the angle. Okay, so this is the dot product. There's another product that we can form, another pairing between vectors. That's called the cross product. So if I have two vectors, v and w, the cross product of v and w is computed as using this funny determinant. Let me give myself some room. So you compute it as this sort of illegal determinant. Illegal because in the top row, instead of numbers, you have the standard vectors, I, J, and K. And then on the second row, you put the first vector, v1, components of the first vector, v1, v2, and v3. In the third row, you put the components of the second vector. So that's w1, w2, and w3. Okay, then you work out this determinant, and then I get I times v2 minus v. Do this little thing. So it's I times v2 w3 minus v3 w2 plus j times. And for the j determinant, so when you're doing the j, you eliminate the first row and the second column. But j is special. When you do a determinant, you want to do the multiplication backwards like this, right? Instead of doing it, cross and back, you do back and go like that. So you get v3w1 minus v1w3. Finally, you add k times this determinant over here, v1w2 minus v2w1. All right, so this is the formula. What I wrote over here is the official formula for the cross product, and it's really it's almost like a soup. It looks very random, a random combination of the coefficients. You build a new. So here's an observation. You start with two vectors. You do their cross product. You get, instead of a number, which is what you got in the dot product. When you do the cross product, you get a vector, right? And the coefficients are these. They're sort of they look like random expressions, use quadratic expressions involving the coefficients of the first vectors. But this is really, these coefficients are not random at all. They encapsulate very useful information. All right, so now let's understand the cross product geometrically. So here are two facts for you. These facts will let us understand the vector. First, what's the length of the cross product? The first fact tells you that the length of the cross product is the length of the first vector multiplied by the length of the second times the sine of the angle between them. So here's the picture. So this is V, this is W, and theta is the angle between these two vectors. Okay, so this formula is similar to the formula for the dot product, but instead of a cosine, you have a sine. So this formula here can be derived from the earlier one, right? It's perhaps even more surprising than the previous formula, because this involves the cross product, which is really crazy looking, has a crazy looking formula, and the thing on the right is more understandable. But it turns out that if you know if you know the geometric interpretation, if you know the relationship between dot products and cosines, you can derive, just with a little bit of work, this formula I wrote here. So this is done in the notes, but I don't want to do it now. It's optional. You guys can look at it and we can talk during office hours. Okay, what I would like to stress, to focus on right now, is that this, in the case of the cross product, the number we get here on the right has a nice geometric interpretation. It's the area of a parallelogram. So area of the parallelogram. Right, let me move this triangle down. Here's the parallelogram I mean. So you start with two vectors, and then you can build a parallelogram just by taking copies of the two vectors and placing them at the, like I just did, right? So this side over here is a copy of this, of W, and this, here's V, and I get a copy of V, but emanating from the tip of W. Then I form this parallelogram from the two vectors, and the length of V times sine theta is the height of this parallelogram, right? So this is this height over here. Let me draw it dashed like this. So the height is V, the length of V, times sine theta. And the base, the length of W gives you the base, right? So here we're multiplying the length of the base times the height, and this gives us the area of the parallelogram. All right, so now we have a good understanding of the length of the cross product. Now let's understand the direction of the cross product. Okay, so here's what it says. So if this is V and this is W, then the right-hand rule is saying that V cross tells us the direction of the V cross W. So V cross W is perpendicular to both V and W. And second of all, that the direction, so if I tell you that a vector is perpendicular to both V and W, it's either this vector or the other one that points down. And the way you tell which is you do the right-hand rule. So you move your hand from V towards W. So you move so you do this. So here, let me try to draw a hand. So here's a hand. Okay. No. Okay. Here's Mickey's hand. So you see, you move your right hand from V towards W. So your four fingers in your right hand from V towards W, and then your thumb points in the direction of V cross W. So this tells, so you know that which of these two vectors. So V cross W is perpendicular to both V and W, and this almost tells you what V cross W, the direction of V cross W, but you get the direction using the right-hand rule. All right, so let me write the other thing that I just said down, namely that if I do that V cross W is perpendicular to V. So, right, so to say that two vectors are perpendicular is the same as saying that their dot product is 0, because perpendicular means cosine, angle is plus or minus 90 degrees, and that's the same as saying that cosine is 0, and that's the same as saying that the dot product is 0. Okay, so the dot product is 0. This equality here is this angle, and the other angle, the statement that the W is perpendicular to V cross W, that's just saying that this is true. And now these two equalities are, I'm saying that if you just start with a general vector V with components V1, V2, and V3, and a general vector W, components W1, W2, W3, if you just take the formula I gave you for V cross W and use the formula, the algebraic formula for the dot product, that's going to give you 0 regardless of what V and W are. And similarly for this other one. So this is boring but easy calculation. right? So the fact that the cross product is perpendicular to V and W is a boring but easy calculation. The hard fact, what I'm really not discussing here, I'd be glad to talk about this during office hours, is that the right-hand rule gives you the correct direction. Okay, so this is what we'll need. So this tells us this is what we'll need about the dot product and the cross product. Now let me tell you about determinants. So the length of the cross product has that nice interpretation as the area of a parallelogram. So the determinant has a similar interpretation, but it's in terms of the volume of a box. And here I drew the general setup. You start with three vectors, u, v, and w. And then using copies of these vectors, the three vectors, you can build a box. And it turns out that the determinant, if I start with a matrix with entries any matrix will have this shape, right? It'll have three columns and the three rows, and the rows I can think of as giving me the coefficients of three vectors. So if I start with any determinant, I can look at the coefficients of the matrix and draw a box like that. And my claim is that this determinant is equal to the volume of this box. Or maybe it'll just be more precise from the get-go. It's plus or minus the volume of the box, because volumes are always positive or non-negative. Some degenerate boxes will have volume 0. If the three vectors live on a plane, then the volume will be 0. But also, volumes are always non-negative, and determinants are sometimes negative. So the only way my claim up top here could be true is if I made some caveat, and the caveat is that the determinant is plus or minus the volume of the box. But still, this gives us a nice we understand the determinant almost completely from this description. Let's see. So this can be understood from our previous work. So let's understand why this is true. So this determinant, let's expand it across the top row. So the determinant looks like u1 times this little determinant, right? You eliminate these two rows and you do that little determinant. So you get u1 times v2w3 minus v3w2 plus u2. Here's u2. You do v3 minus, you do the 2 by 2 determinant backwards. So you get v3w1 minus v1w3 plus u3 times, so here's u3, you eliminate its row and column, and then you do the 2 by 2 determinant. So that's v1 w2 minus v2 w1. Okay, so I just wrote out the determinant in full, expanding across the top row. And now let me observe that what we got is the vector u multiplied by the cross product of v and w. Right? So here are the three coefficients of u, and here are the three coefficients of v cross w, and I'm adding the products of these coefficients correctly. So the matching coefficients and adding everything. So that gives us the dot product. So this observation gives us something to work with, so geometrically, right? So let's look at this. So let me draw v cross w here. So v cross w is perpendicular to v and w, so it's going to point up like this. And u times v cross w, u times this cross product is geometrically the length of u times the length of v cross w times the sine of the angle between them. Okay, so let me draw we call theta this angle over here. And that's the formula that we have for the dot product. Now, let's observe that the length of V cross W is the area of the parallelogram, of the base parallelogram. And u times sine theta is this height over here. If I multiply this length by sine theta, I get this height. So here, the height is the length of u times sine theta. So here we have the height. And so you see I'm multiplying the area of the base parallelogram by the height of the box, and this gives me the volume of the box. So this is the volume. Okay, I'm kind of running out of space here. I want to stay here. So let me just say that this is the volume. Okay, now there is an issue, right? I told you at the beginning that the determinant was equal to the volume of plus or minus the volume of the box, and I just showed you a derivation telling you that shows us that the volume is the determinant is equal to the volume, but no minus sign appeared anywhere. On the other hand, we do determinants if we experiment a little bit with determinants, we'll see that sometimes the sign comes out negative. So there must be a problem with this derivation, right? Because the derivation, no sign appeared in the derivation, and so the conclusion was wrong. So let's see where we missed this sign. So in the first step, this equals sign, that's fine. Nothing wrong happened here. It just expanded along the first row and I did it correctly. The second equal sign is also true, also correct. Nothing wrong happened here, just algebra. Just a definition of the dot product and the cross product. Next, what happened over here? So V cross W is the area of the base parallelogram, that's okay. Now, u times sine theta actually may not be the height. So u times sine theta is actually plus or minus the height. So here's the reason. It could be that u was actually pointing down like this. That the vector u was below the plane spanned by v and w rather than above it. Right? It was on the other side of this plane when compared to v cross w. So if that would happen, the angle that we need, so the angle that appears in the cross product would be this whole big angle over here instead of this little angle that I have in the picture. And for that big angle, the sine, so the sine of the small angle and the big one, they differ by a sign. So that's why u times sine theta is plus or minus the height. So it's going to be plus if u and v cross w live on the same side of the plane spanned by v and w. So that's why this gives us plus or minus the volume. Okay, so that's it. This is all that we're going to need. This is some interesting geometry, and this is also all we're going to need about vectors in this course moving forward. So let's go on to the second topic of today's lecture, and that's the area of a graph. So this is an application of double integrals. So here's the setup. I have a region of the plane, I called it D. I have a function f of xy, and then the graph is this set of points in the xyz space where the last coordinate, the new coordinate c, is equal to f of the first two. All right. Now, our task is to figure out the area of this curved shape. So here's how we're going to do this. I'm going to subdivide the area of this curved shape of this graph into little pieces, but these pieces will be special. So what I'll really do is I'll subdivide D into little pieces. So let me draw this permanently. I'll subdivide D into small pieces, and then look at the corresponding pieces, parts. Take a little piece of area inside D, and look at the corresponding piece of this graph that lives above it, like this. Okay, then what I'll do is I'll assume that the piece at the bottom is really small, and then it'll have some area, delta A. Then I'll relate that area to the area at the bottom, at the top. So it turns out that this area over here will be bigger. So this little piece of surface, little piece of the graph, covers this little square at the bottom, rectangle at the bottom. So this area here will be bigger than the area down there. So I'll just figure out by how much it's bigger. So what's the multiplying factor? So how much bigger this is than that is. And then I'll do a sum over a bunch of little pieces down here, but then I'll multiply the area of each little piece by this multiplying factor to really get the area at the top. So this sum will be an integral. All right, so let's start annotating this picture with a bunch of information that will be useful in our calculation. So first, let me just call the width and the height of this little rectangle delta x and delta y. And let me call this point over here, let me say its coordinates are x0 and y0. And let me just say that this piece at the top has, let me say the piece at the bottom has area delta A, so delta A is equal to delta x times delta y, and that the piece of the graph that sits above this rectangle in the xy plane, that this is area delta S. And our job is to relate delta S with delta A, assuming that delta x and delta y are really small. The dimensions of this rectangle are really small. To do this, I'm going to zoom in to the picture. Oops, zoom has two O's. Let's zoom into the picture. Let me draw this curved rectangle, if that even makes sense, on the graph, really big, so we can talk about it. So here it is. So for example, this point here is the same as this point over here. It's the point on the graph that lies above x0, y0. So this has coordinates x0, y0, f of x0, y0. Okay. And for example, this point over here, that in our original picture, it's that point. It lives over this other point over here, which so y is the same. Y is also y0, but x is x0 plus delta x. It's a little bit, x is a little bit bigger. And we'll also pay attention to this other point over here. Here it is in the little picture, in the original picture, and there is the point in the xy plane that lies below this point, this marked point. Okay, we'll also for our analysis, we'll also look at two vectors. So we'll call this one A. So A points from here to here, and B is this other vector that points from here to here, like that. Now, we'll look at A and B. We'll get very good approximations for the lengths of A and B. And then this will give us, using the cross product, a good approximation for the parallelogram spanned by A and B. And that's very close to the area, to delta S, to the area of this curved rectangle. And so this really good approximation is what we'll use to compute the area of the surface at the end. Now let's work out what A and B are. So first, the exact formula for A is the coordinates of this point minus the coordinates of that point. Okay, so what's the difference in the x-coordinates of these 2 points? The difference in the x-coordinates of these 2 points are is this difference here in the x-coordinates, that's delta x. Now, what's the difference in the y-coordinates of the 2 points? It's nothing. Both y-coordinates are y0. Now, what's the difference in the z-coordinates of the 2 points? Well, the z-coordinate of the tip of the vector is f of x 0 plus delta x comma y0, and the z-coordinate of the source of this arrow is f of x0 y0. So there you have it. Oh, I broke my rule. I said that I would draw vectors with square brackets, but here I had round brackets, so let me correct that. Okay, now I have square brackets, angle brackets. Good. So that's the exact formula for A. Here's an approximate formula for A that's convenient for calculations. So I'll just say that the first coordinate is delta x, the second coordinate is 0, and this difference. So here I'm looking at the difference between two values of f. If I divide it by delta x, I get the x partial, df dx of the point y0 y0 x0 y0. So this difference divided by delta x would be this partial. So if I multiply the partial by delta x, I get a number that's very close to that difference. And it's okay to do this approximation here because we're taking delta x, the dimensions of the rectangle in the xy plane, to be really, really small. Okay, now similarly, now let's look at B. So I'll just give you the approximation for B right away. Okay, so the coordinates, so B, for this vector over here, the first two coordinates are the same as the first two coordinates of this arrow down here at the bottom. Right, so the x-coordinates of the two vectors are x0, are the same, and the y-coordinates, the difference is delta y. So B is 0, delta y, and then the difference in the z-coordinates, for very similar reasons, the difference in the z-coordinates are just approximately the y partial at the point, at this point over here, the top left corner of the rectangle, the y partial times delta y, right? Because the difference between these 2 points, so the x coordinates are the same, the y coordinates are a little bit different, and so the height is going to depend. So the change in the height is really the difference in these values of f, when y is a little bit different, but x stays the same. That's a y partial. And then you multiply that by delta y as before. Okay, so now the area of the parallelogram, right, looking back at this picture, the area we're interested in is really close to the area of the parallelogram spanned by A and B. The area of this parallelogram can be computed as a cross product. So delta S, let me just write everything down. So delta S, the area of this curved rectangle, is approximately the length of the cross product of A and B, right? Because this is the area of the parallelogram. I hope I broke the way I broke the word is okay, is grammatically correct. Now delta S is this the length of this cross product. Now what's this cross product? It's so let's work it out over here. So A cross B is approximately, so let me just put I, J, and K at the first, on the first row, along the first row. Now in this second row, let me just put the approximate value we found for A in the previous page. So that was delta x 0 and the x partial times delta x, right? So f sub x is just the x partial and even here I'm omitting the point where I'm evaluating the expression. F sub y is the y partial. I'll just omit the point where I'm evaluating the expression. Now let me put in the third row the approximate values for the components of b. So that's 0, delta y, and f sub y dot times delta y. Okay, now this determinant, so the I component is 0 times, it's this minus that. So that's minus f sub x times delta x delta y. Let me put delta x delta y at the end. Now j times this, so 0 minus f sub y delta x delta y, so minus f sub y, and delta x delta y is at the end. And then finally the k component is delta x delta y minus 0, like so. So just get 1 times that. And so the area of this parallelogram, this is approximately, so the length of this cross product is, so the cross product is a number times another vector. The length of a number times a vector is just that number times the length of the vector. I mean, this is a positive number, so we don't need to put an absolute value there. So this is just, now the length of this vector, that's the square root of the x partial squared plus the y partial squared plus 1. You don't need to write 1 squared times delta x delta y. Right, so delta x delta y, remember, was the area of the rectangle on the bottom. And here I'm omitting the points where you have to evaluate the partials. The points are x0, y0. Okay, so all this derivation was to reach at the following conclusion. So the conclusion of all this, maybe I'll put the conclusion on after the end of the calculation. So the conclusion is that the area of the graph is a kind of is a surface, is a curved surface. So the area of the graph of the function of f over a region D of the plane, that's equal to the double integral over D. Oh, I'm running out of space. So let me rewrite this. Area of the graph of f of xy over D, D is a region of the plane, so this area is equal to the double integral over D. So we're adding over a subdivision of D, this number, so this scaling factor, f sub x, f sub y squared, f sub x squared plus f sub y squared times plus 1 inside the square root times dA. Right, so dA gives you the area of a little piece of D, and here's a scaling factor that when I multiply by the area of that little piece of D, I get the area of the portion of the graph that lives above that piece of D. When I add these areas, when I add all of these numbers together, I get the area of the whole graph. So that's it for the derivation. Okay, so to conclude today's lecture, I would like to do an example calculation. Let me check in my notes exactly the numbers, the formula, the function, and the shape. So here's the example calculation. So we'll compute the area of the graph of the function f of xy equals x squared plus 2y. But we're looking at this function over the region, over a rectangle. So here are the two axes. The region D is just this triangle with coordinates with vertices 0, 0, 1, 1, and 1, 0. So that's our region D. Okay, so according to our discussion, the area of the graph is equal to the double integral over D, over this rectangle of the square root of the x partial of f. So the x partial of this function here is 2x squared plus the y partial of f, that's 2 squared, right? The y partial, the derivative of 2y with respect to y is just 2 plus 1 with respect to dA. And so now so the thing inside can be simplified. So the thing inside the square root is 4x squared plus 9, actually plus 5. And we're integrating this over this rectangle. So let's do this integral. It turns out this integral is easier if we do it in the order dy dx. So here we'll have a y going from, actually x going from something to something, and then y from something to something. And then you have to put in the root of 4x squared plus 5 dy dx. So in this example, the bounds for x are, so the minimum value of x in this whole region and all of D is 0, and the maximum value of x in the whole region is 1. So these are the bounds for x in the region. So x goes from 0 to 1, and y, by fixing intermediate value of x, y is constrained to this vertical segment. So y starts at 0 and stops over here. Now, so y you can see is on this line that joins 0, 0 to 1, 1. The equation of this line is just y equals x, right? Because this is a linear relationship between y and x, and it's satisfied at both at the origin at the point 1, 1. So this equation is the correct equation for the line. So y starts, so for fixed value of x, y starts at 0 and stops up here where it is equal to x. Okay, now let's evaluate the two integrals. We're integrating x from 0 to 1. So the integral inside, you can see that this thing here, the integrand, doesn't depend on y, so it's a constant. You can just pull it out of the y integral. Then I'm left with the integral of dy, that's just y from 0 to x, that's just x. So the integral of dy from 0 to x just gives me x. And now the integral we have here is a friendlier integral, is actually okay, because you can see that here x is almost a derivative of what's inside, so we can do it with the use substitution. So let's do it with our minds. Let me move to the next page. So we're looking at the integral from 0 to 1 of square root of 4x squared plus 5 times x dx. So this is, we can just evaluate this. So this is something to the 3 halves, right? This is going to be 4x squared plus 5. So previously I had 4x squared plus 5 to the 1 half, but now the integral will be this to the 3 halves times, so if I differentiate the thing I have over, to divide it by 3 halves, right? You just divide by the exponent. So next, when I differentiate this, I want to put a constant to make sure I get the original thing. So when I differentiate this, I get the square root times the derivative of what's inside here. So that derivative is 8x. Originally, I had a single x, so I'm going to divide by 8. So the way I'm going to divide by 8 is just multiply the denominator by 8. So okay, so you see when I differentiate this, I get exactly that, because you drop the 3/2, which cancels here. You get a 1/2, so that's the original exponent. Then you multiply by the derivative of what's inside. That's 8x. But here I'm dividing it by 8, so I'm just left with x, which is exactly what I had before. Okay, now we evaluate this with x between 0 and 1. That gives us, okay, let's do, so first there's this whole constant. So there's 24 divided by 2, that's 1 over 12. And then a certain expression. So what I'll get is, first I'll substitute x by 1. I get 4 plus 5, that's 9 to the 3/2. So 9 to the 3/2 minus what I get by plugging in 0 in place of x. That's 5 to the 3/2. Okay. Now, the answer is not as good as it could. So this is a number. So if you could say that we're done, but we're really not done yet. So I believe the expression should be written in as simple form as possible. So what makes me unhappy about this answer is these fractional exponents, which people may not be able to understand. So say you're an engineer working on a technical problem, and this is the answer you get. If you're going to tell this answer to some manager who may not have as much familiarity, comfort, be as comfortable with mathematics as you are, these exponents may put that person off, tip them off balance. So let's just write this in as simple possible. So write an exact answer, but in simpler terms. So let me just do that. We get 1 over 12 times 9 to the 3/2, that's 9. 9 to the 2/2 times 9 to the 1/2, that's root of 9. Minus same thing here, 5 times root 5. Of course, root of 9 is 3. And so 9 to the 3/2 is 27. Okay, so this is an answer I think is more directly understandable than the previous one. And that's what I'm going to box and call my final answer. So in exams, I encourage all of you to write as easy, simplify your answers as much as possible. Bring it to as in early school. If you can write your answer in terms of first grade mathematics or third grade elementary school math, that's something you should do. Okay, so this is the example I wanted to do with you. This concludes what I had to say in today's lecture. Thank you for listening, and I'll see you guys next time.